First and foremost, welcome again to our webinar today, right? Talking about the near future of databases, right? So my name is Richard Koh, and I'm the chairperson for our free and open source software SIG, part of SCS. And I'm actually very glad that we have here with us today Yoshi, right? Yoshi is the APAC regional data architect, right, from DataStax. Yeah, my apologies, Yoshi. Yeah, and to kickstart this today's session, right? I think all of us know, right, that databases has been around for a long time, and most of us will be very familiar with relational database, right? I almost like grew up with it, right? Seeing how it has been pretty much the lifeblood of most applications, especially for transactional ones. However, with the rise of Internet of Things, big data, and the increased use of cloud-native applications, this has sort of like created new challenges for relational databases, right? Typically, such databases are not able to handle new varieties of data very well, right? That we use, more and more in today's world, right? Things like non-transactional data, for example, feeds from social media networks, images, so on and so forth, whatever you call, right? And, as long as it's non-transactional, it's going to be a challenge for relational databases. And often, the structured nature of relational database systems, right, become a bottleneck in many scenarios. And this is the reason why there's a drive for a need, right, of unstructured, schemaless, non-relational databases, which has become very popular recently, right? And today, thanks for Yoshi, right, joining us. We will be able to look at why NoSQL technologies are quickly becoming the leading choice in terms of addressing business needs. And definitely he's going to share with you what is the near future of databases going to be like, right? So with that, I'm going to hand it over to Yoshi. Yoshi?
Sure. Okay. Good evening, everybody. Thank you for attending. So this evening, I'm going to talk about the near future of databases. Well, as Richard said, we all know about databases very well. And presently, I'm going to talk about sort of the history and the sort of status that we know as of now. Probably most of the audience are from the industry, so you have already have actual hands-on experiences, as well as talking to the vendors, as well as your colleagues or some people outside. You have all the information that you have been gathering. But this is a session of sort of trying to take things or make things into perspective and to understand where we are now. And as my personal experience and the personal experience of talking to people or understanding the status of the things that are going on within the company, as well as on the open source world, to understand where we're sort of heading to. Okay, so first of all, I will start off with what we have had in the past and what is in the present. So understanding the past sort of brings us to why we are in the present state. Okay, so first of all, when we hear the word database, so when we hear the word database, what does that mean? Basically, it's a collection of data and information. Well, if it's just data and information and it's just like, I don't know, files or some storage, that's just really not a database. But usually when you hear of a database, it's somehow organized. Even if you say it's a schemaless type of thing, it is organized in a way that you can handle, right? So that's another aspect. And of course, you would have a way to store, retrieve, modify, delete the data or the information that is in the database. You would have some access methods, or you might have some specific languages like the structured query language or any other types of language, or certain frameworks that would allow you to do these kind of operations. And of course, you would have your management system where you would have um, the structure to manage your database itself, create one, remove one, do backup and restores, do some access management, defining roles, defining users, and that kind of thing. So basically, when we hear the word of databases, these are some of the concepts that you would have in mind. And these would be some of the points that when talking about databases that you would have in mind thinking about it. But usually when we say databases, as Richard said, we normally think about relational databases. So relational databases is like already 50 years from its inception. And it has been the dominant database, type of database, and it still is. And usually the dominant language in the database is the structured query language or SQL. Or maybe you have some frameworks that would emit SQL queries to interact with the database. And then you have database management systems that you would run with the database. Okay. But then about 10 to 15 years ago, there were some changes that came to the world, or maybe even more before that. Actually, there was like 30 years ago, there was a start of that kind of change that happened. So the change is the internet. Well, actually, it's not just the internet, but internet is sort of like symbolizes the change, right? So initially, when we had communication systems, and then we had like bulletin board system where you had a centralized server, and you would dial up to that server, and you write things there, and people read those things. And then you also had like UUCP-based service, the Unix to Unix copy systems. So those are more like between organizations. So organizations would have a centralized server, and people would be interacting with that to have send mails or write news and that kind of thing. And the data would be passed on from organization to organization. Right. And then there was some government-funded type of projects like the ARPANET or CSNet, which started to sort of bring the internet to the world. Well, basically, it was more like a military project, but then it was exposed to the academic world where people started using it. And then eventually that sort of opened up to the commercial world as well. And so that also started to bring in a lot of other people. And that also brings in the standardization like TCP/IP, and also people started to share a lot of information. So there was some ways to access the information, how you would share the information. Well, of course, you had the mailing system and you had the news bulletin systems and that type of thing, but also you had like the network file systems like NFS, or you had like things like Gopher where you would try to find things. And then, of course, the very famous HTTP came into the hypertext came into the picture. So you would have the World Wide Web Consortium created and standardizing the way to share information within the internet, and of course the domain name systems as well. So these are some of the standardization and the platforms that were happening. And of course, along with that, you would have all the information about, well, you have all the hardware that is coming with it, becoming personal computers becoming um, more general thing to the general public. And you have, rather than mainframes, you have like workstations and you have like laptops coming out and that sort of thing. So those are all contributing to the way that people interact with each other and also the internet. And the amount of data is just growing and growing. And then there are some, of course, the service providers that provide you with their connectivity to the internet would start providing you with more, for example, dedicated lines. So it's rather than doing a dial-up from time to time, you would have an always connected kind of service, and internet service providers would flourish. Then, of course, the abundance of the data would sort of provide a foundation for people trying to find where the data is. So, for example, web portals like Yahoo or Google or MSNet or AOL, all those kinds of things started to start out. So there's all of these show how the abundance of data is coming out from the internet and how things are proliferating from there, right? So, and based on that, the requirements started to change. So there's an immense amount of data that is produced, and it's not just by hands, like it's not just by humans. The machines itself or the device itself are starting to emit data or information. So there's an immense amount of data that is coming out. The other notion is that there is the concept of or the understanding that internet never stops. Basically, it's a sort of a fault-tolerant network in itself, and everything is always on. You expect to access something, and you are able to access something any time of the day. And another thing is that it's a global thing. It's a global reachability, meaning that there's no work hours in the internet. Basically, every hour is a work hour. So basically, you would expect everything to be accessible always on. And another thing is that people are expecting more lower latencies these days. The thing about it is that when you provide services, you would have services near to the users of the services, which means that you have your data centers in your regional areas where people have access to that data centers. Okay, so these are sort of the requirements that have popped up with the internet coming on, and also the proliferation of that kind of hardware and infrastructure. Right. So to cater to these requirements about immense data and the capability of being always on or having a global reach or providing a low latency, um, sort of boils down to a couple of things. So one of them is horizontal scalability or like distributed workloads. So the thing is that rather than bringing in larger and larger machines to cope with the amount of data, it's more about having multiple machines to handle them. Distributing the workload among the multiple machines, distributing the data among the multiple machines. So it's basically a horizontal scalability type of way to cater to the amount of data. And of course, the scalability, horizontal scalability would also translate to having your services distributed in different data centers around the globe as well. So that also sort of would come from the concept of scalability globally, right? And also the low latency part is helped by having the workload distributed to multiple different servers or nodes, right? The other thing is redundancy. So in order to provide a sort of an always-on architecture means that you don't want to have a downtime, which means that there needs to be sort of a mechanism to provide a way to be resilient. It doesn't mean that you have one server that is like a hot cold type of standby, which produces some kind of switchover timing where there's a time where things are not available, but more like it's transparent. You don't need to think about a downtime, which means that you have multiple servers and you have same copies of the same data as well, right? So even if you would expect machines to go down if you have many of them, and even with those machines going down, you would want to still be able to access the data that you are trying to access. So having multiple copies of the same data is another way of providing the always-on capability. Okay, so in order to cater to these requirements, you have this kind of horizontal scalability and redundancy. You would need to have that embedded into the database itself. So when you think of the way that it had been done before and after the proliferation of the internet and the abundance of data, you could think of a way that there's a different type of architecture nowadays that are providing platform for the databases. if you think on the legacy side, it's more of a scale up type of architecture. But on the more modern side, it is more of a scale out type of architecture. Of course, you could do multiple, well, horizontal scalability using the legacy type of databases by using techniques like sharding. That kind of thing is also possible, but it is more of like an afterthought type of way of handling that type of thing. Another thing is, of course, even now, I would say that the relational way of thinking is, well, because we have already the technology or the techniques to use that way of handling the data, the SQL language will still be a strong language to use for the database, but there are other things that are coming as well. And as you can see, the more modern things are more basically come from needs of internet companies, and those companies are sort of in a way, say, create more open source type of things. So things like Cassandra or Redis or MongoDB are basically open source. Hadoop and Spark are open source as well. So rather than the proprietary type of things, the more adaptable, more low friction to entry is provided by the open source way of things, right? So as I am from a company called DataStax, and maybe you may know or may not know, we do provide the support for Apache Cassandra, which is the open source NoSQL type of database. Probably you have heard about it, and I'm going to talk a little bit about it just as an example of the modern type of infrastructure, right? So the core characteristics of Cassandra itself is that, well, it naturally has a zero downtime architecture. Well, it's open source, so basically it's zero lock-in, and the global scalability provided by its architecture is also there. And there's a lot of companies, basically internet companies, that have been using Cassandra for a long time. One of the famous ones would be Netflix, Spotify, Instagram. Yahoo Japan has a lot of them as well. Payment systems like Venmo or Monzo have been using Cassandra as well. And of course, it's not just the internet companies that are handling the huge amount of data that is using Cassandra, but also the enterprises are looking into or feeling or understanding the value of the zero downtime, zero lock-in, and global scalability. So companies like FedEx or Macy's or PayPal, Verizon are using Cassandra as the data platform of choice. Okay, so I'm going to talk about a little bit more about Cassandra itself, how this is done. Okay, so when talking about Cassandra, Cassandra is a peer-to-peer architecture. It's not sort of what we call a leader-follower model or a master-slave model, where you would have one leading machine, and there will be some other machines that will be a replication of the data that is in the master, and the master would be the machine that would accept all the requests or the right request, and then replicate that to the follower machine types of things. It's more of peer-to-peer architecture, which means that any of the machines would have the same functionality. I'm saying machines, but actually in Cassandra, we call them nodes. And nodes are, well, in Cassandra, well, Cassandra itself is a Java program. So actually it's a JVM instance or a Java program instance running. So we call this a node. And each of the nodes have exactly the same functionality. So you could contact any of the nodes to interact with the database. So a group of nodes can be grouped into what we call racks. and the racks can be grouped into what we call data centers. And basically, these are basically a name for a group of nodes. It doesn't necessarily have to map to a physical rack or physical data center. It's just a name for a group of nodes. And then the group of data centers, we group them into what we call clusters. And this cluster is one single database, which means that you could access any of the data centers and any of the nodes in any of the data centers, and you would be contacting that same database. The data model itself, or more in the near physical layer, actually it's a wide column store, which means that it's sort of like a key value where you have a key and then the value. And then within that value, you sort of have like a secondary key value. So you have like a double key where the combination of these key would identify a single row, right? So, and then as a presentation layer, we have tables. So basically you have rows and columns, which are familiar to the RDBMS as well. The only difference is that basically it's a presentation rather than the structure, right? One thing is that you would access with your key and you get your attributes when you do a select. Interacting with the database itself, you would use the language called CQL, which is the Cassandra query language. And it is basically very similar to SQL. So you could do your selects, you could do your inserts, you could do your updates, you could do your deletes, right? So that is sort of the basics of Cassandra itself. But then we need to talk about the architecture, how the zero downtime is achieved. So as I said, any application can contact any of the nodes within the cluster. So when when the application contacts a cluster, well, it would shoot off a request to the node, right? And then within the cluster or within the data center, you could define how many copies you would have within that data center. And you have, which we call the number of copies is what we call a replication factor. And for example, if you define that within this data center, I'm going to have 3 copies, then any write to that data center defined in the schema, well, it's defined at the schema level, any write to that data center would always have 3 copies. So for example, if our application writes, provides a request to the database, what actually happens within the database is that the writes will happen all at once. So there's going to be 3 writes to 3 different nodes within the data center if you're going to have 3 copies, right? So any reads and writes would go to those 3 copies. Nice thing about it is that even if one of the node is down for some reasons, maybe it's a network glitch or maybe it's a hardware error or something like that, you still have 2 other nodes there to read and write from, which means that even if a node goes down, you still have your availability. And then when your node comes back up, it sort of has an auto-healing facility where the data will be synchronized to the node that was down for some time. This could be also mapped to the cloud. So if you have like cloud regions and you have availability zones, you could map the copies to the different availability zones so that even if an entire availability zone goes down, you still have 2 other copies that you can interact with. So this provides the basis for zero downtime at the data center level. But of course, as I said, you could have a horizontal scalability, which means that you could have multiple data centers, right? And the data centers can talk to each other. Because it's a Java program, you can run it on bare metal, you can run it on a VM within a bare metal, you can run it in a VM in the cloud, which means that you could have a cluster that would span on-premise and the cloud as well. So basically, you could have some of the applications reading and writing on on-prem, some of the applications reading and writing in the cloud region, for example. And then, of course, the data centers the data between the data centers are always replicates. Actually, when a write request comes from applications to either of the data centers, the request would also be forwarded to the other data center as well. So the write happens at the same time. And you would have the same number of copies. Well, you define how many copies you would want to have in each data center, and then the writes will happen to those copies as well. Okay, so sorry. As I said, you could still increase the number of data centers as well. So you could have multiple data centers across the globe as well, which also provides or contributes to the zero downtime. So for example, there might be cases where an entire data center goes down and the application might not have a place to connect to. But in this case, usually you would want to switch to another data center on the other side. So, which also provides you with a zero downtime capability, right? So this peer-to-peer architecture and having the automated replication functionality in the database itself provides you with the zero downtime functionality. So Apache Cassandra has this functionality from the get-go. And this has been started by a lot of internet companies, but also a lot of enterprises are using this now as well. Okay, so this is like the current state. We talked about the RDBMS, we talked about how the new types of more scalable databases like Redis and Mongo have come out, and they are now getting accepted and being used in various places in the world. Okay, so there was a question about when switch from one data center to another data center, what happens to the thread or processes handled by that data center? Okay, so the thing is that it will be up to the application to handle the error or detect that a data center is down. It may be the application or it might be the load balancer in between the at the application side. And so the thread itself will sort of, what we say, result in an error, I would say. So it may be up to the, well, that means that you have sent a request and the data center goes down, you don't have a response, meaning that it either times out or you get a bad request kind of response. So in that case, if that error sort of suggests that the data center itself is down, you might switch over to the other data center, or the load balancer you might switch at the load balancer level, kind of thing. But from the database perspective, the database is still running. So as a database, there's a zero downtime. It's more of the switch off by the application side. Okay. There was another question about the replication. Well, how real time is the replication? Probably is the question, I would say. We have been having customers doing replication to multiple sites around the globe. One of the users that I know of has 5 data centers, 2 in the US, 1 in Europe, 1 in South America, and 1 in Asia. And they specified to have 3 copies in each data center. So this 3 times 5 means they have 15 copies of the same data. Of course, if you're accessing the local data center, your contact will be the local data center, but at the same time, all that request would also be forwarded to the other data centers as well. at the same time. And the piece of the copies will be sent to those data centers as well. So, which means that basically it's more about the physics of how fast the electrons can travel. So there was some people who had done tests saying that I'm writing 10,000 requests per second and reading 8,000 requests per second. I mean, 10,000 requests and 80,000 requests per second, and doing that in each data center. And they sort of wanted to understand how fast the data would be synchronized in all of the data centers. So having the latest data in all of the data centers. And well, basically it's like under a second, somewhere around 650 milliseconds to maybe 350 milliseconds to 650 milliseconds. So probably the farthest path they had to travel was from the Asia data center to the one in South America. And that took like probably 650 milliseconds to get an acknowledgement back. So that is the sort of the speed that we are thinking of. Well, of course, the connection line would have to be that kind of, have to provide that kind of reliability, of course, but that is the sort of expectation that one would have. Okay, so there's other questions like how would you determine whether Cassandra or MongoDB is a better choice or NoSQL DB? So there's well, the Cassandra probably is more about availability and multi-DC. Mongo also has that. I think currently, as I know, it's probably similar to a multi-master type of way of replicating. I'm not quite sure about that, but the thing about Cassandra is that you could basically scale by adding nodes and have multiple data centers, and you have your copies in all those multiple data centers if you want to have them. The other thing is that you could say that I want to have these tables to have copies in the other data centers, but these tables don't have copies in the other data centers. Okay. So that's one of the things that might be sort of the criteria for a choice. Another question that I see is about the manpower of maintaining the nodes. Okay, so this in a way would sort of depend on the skill sets at this time. But then also there are, I would say, things that are coming forward to make the maintainability of the clusters much easier. For example, I think Netflix had like 3 people maintaining thousands of nodes. And one time there was an incident where, well, they had nodes in Amazon, I think, and Amazon did a reboot of multiple nodes without letting them know. And they had to cope with that with like 2 people over the weekend. But then there was this resiliency that Cassandra provides that you could still keep on with your service while you control or manage each of the nodes going up and down, right? So it's well, it would really depend on how much you understand and how much you have automated things. The way the automation is coming is something that I'm going to talk from now when I'm talking about the future, right? Okay, so this is more of the crux of the talk today. We are going to talk about the future. So when we're talking about the future, we have to go back to where we came from, where we are thinking of what a database is. It's a collection of information, data. You would have a certain kind of structure. You would have a way to access the structure or the data, and that kind of thing. So you putting that, you would have that in the back of the mind when you think about the future as well. So things that are impacting the future of the database, I would say we could categorize that into like 4 things here. So one is data, one is cloud, one is open source, and one is analytics. Okay, so data. So the data itself is growing. Everybody knows this, especially the people who are listening to this. And it's growing at a fast pace, like really fast pace. This graph is from research done by Bond, and it's called the Bond Internet Trends, but basically it's derived from the research done by IDC. And it's basically saying that you're going to see a lot of data coming in. And it's not just unstructured data, but structured data as well. And the thing is that the same data, there's original data, but there's also replicated data to cater to the various needs. Another thing is that there are structured data as well. Why there's the abundance of structured data coming in is because of the way that we are looking into the data. So I'm going to talk about it a little later on again, but there's this analytical aspect, you see? So when you do some kind of, well, if you're doing some machine learning type of things with like data, then presently you would want to have clean data or structured data. So that is sort of providing the influx of that data abundancy. Okay. The other thing, well, I've talked about data. So you would understand that the data is still growing. And with 5G coming, it's going to grow even more, I would say. You would have more devices emitting data. And of course, the speed of them coming in would even be faster. So the other point, cloud. So nowadays, cloud is like you have a cloud already. You have your cloud vendors, and the IT industry people or people in this industry are experiencing the cloud already. So they have a perspective. And of course, everyday users are also experiencing the cloud experience provided by cloud vendors, right? So there's this sort of cloud experience from the data level as well. So what are the cloud experiences? So it's basically about provisioning, resilience, and access. So provisioning, so it has become a utility, right? It provides you a way to provision your platform for the database much easier. You don't have to wait months to get your hardware. You could start small, grow big, and shrink again. So this kind of provisioning is one of the things that cloud experiences are bringing. Another is resilience, right? So things that you have like multiple availability zones to cater to your needs of resilience. You could have multiple copies, and then you could have multiple data centers in multiple regions. Right? So that provides the resilience factor. And another is the access factor. So the thing is that, well, if you have a connection to the internet, you would have your cloud vendor providing your database as a service. And what you do is just click buttons and provide names, and then you'd have your database. And then you'd have your interface to the database. It might be some SQL interface, or it might be some REST interface, or it might be some other interfaces. So you already have that kind of cloud experience, and more people are experiencing that day to day. Probably in this region, in the APAC region, um, the taking up of the cloud by the enterprise is coming step by step. I don't say it's that far yet as I'd see in the US, but it's coming. People are seeing more value in the cloud. People are feeling more safer in the cloud as well. So people are moving things into the cloud. But of course, there are things that people would like to keep on premise as well. So the thing is that you would have cloud experiences, but you would want to expect things like the cloud experience on premise as well, right? Well, I talked about the access aspect of the cloud experience. Accessing the data layer, whether it's in SQL language or the REST API or the JSON API or the GraphQL, or maybe even the gRPC or other types of ways of or interacting with the database, or maybe even some frameworks like the Spring Boot framework or the Spring Data framework type of things. Or maybe you have a language with an object or mapper functionality where you could define sort of like domain-based types of ways to access the database, right? So there's a abundance, or well, let's say people or users or developers who are using these various methods to access the data, right? So these are the things that are also coming into mind of the database side, that people have many ways to access the data. Another aspect is open source. So open source has driven the adoption of modern frameworks. So of course, it started by the Unix system. You had the BSD Unix, the Berkeley distribution type of things, where, well, Unix started out as the ATM System 5 or something like that in the old ages. But then there's the BSD, and then there's the NetBSD, and then there's the Linux. And you have the Linux Foundation. And of course, from the World Wide Web app perspective, you would have the Apache Foundation providing the Apache server first, and then you would have all the various Apache projects around the world, right? And then, of course, the new foundation providing another different type of open source, right? So open source has really driven modern software, providing a lower hurdle to jump over to get into new technology, right? And this will not stop. More innovation comes from looking at other people's code, and people want to contribute to make things better because, well, need is and sort of, if you have requirements or if you have needs, you would want to implement that, or somebody would want to implement that. Okay. So one last thing is analytics. So things that if you have data, it's not just you have your data. You push in your data, you keep it there, you build it out. It's not just that. You want to have some things you want to understand from the data itself. So maybe you want to do some reporting using SQL. You want to use your BI tools to slice and dice the data that you have. You want to maybe understand how things are connected through the graph theory type of approaches, or you could do machine learning types of things. So based on the information in the data, you would abstract or get some understanding of how things will trend or how people are looking at things, or understand the shapes of data or find patterns of data or features. And based on this feature, do you want to react to something, for example? So there's this analytical aspect. The thing about this analytical aspect is that I'm not saying there it is now, but as I said, the amount of data that is increasing is not just that the data that is um, produced by human beings, but as I said, it's produced by devices. But the other thing is that also the database system itself does emit a lot of logs, right? So understanding these logs in a analytical manner would provide something for making the operation aspect of the database itself better in the future, I would say. So these kind of aspects would sort of dictate where the database is heading towards, right? So this is sort of a, I would say, a prediction, I would say, but basically where the database is heading is more to provide a cloud native experience. So provisioning a database would be more like a cloud experience, and probably you would have more like a serverless aspect where you could have um, the layers of the nodes handling the actual workloads, and then there's the storage layer. So these could be expanded and shrinked in a separate manner, and elastically. That's another part. And then, as I said, as more of the machine learnings or AI types of learnings are applied to the database logs or the things that the observability of the database are providing, um, the databases would sort of start to self-optimize. Well, of course, you have query optimizing that sort of things, but more of the management side of self-optimizing or doing an auto-resiliency type of things. The key is that it's not just in the cloud, but this will also become an on-premise thing. And also the key to this is where you see the logo here, it's the Kubernetes type of things, right? The Kubernetes, well, the nice thing about Kubernetes, well, the base comes from the technology of the containerization, like Docker, providing a state where you would have a component where you have all the dependencies already defined there, and it's a complete package. You don't have to mix and match things to try to make things work. You have a Docker component or a container component that just works if you bring it up, right? And utilizing that. And then the Kubernetes world is that you would define a state, an ideal state of an environment. And then the Kubernetes environment would handle the components to bring those components into that ideal state. And when there is a degradation from that ideal state to a certain state, we try to get back to that state. So this becomes more of a hands-off type of operational management, where the self-optimization type of things, as well as this the observability that Kubernetes provides, and then the resiliency that Kubernetes provides will help in that aspect. So this type of thing, or this type of architecture or functionality is where I think that the database world is heading. I think you already know, well, if you're using Red Hat and you have OpenShift, you have that kind of easy management interface type of things. Probably the other vendors, for example, VMware, you would have like Tanzu is heading in that Kubernetes type of framework. And also you would have the cloud vendors also providing this GKA and AKS and all those Kubernetes environments. So you would have sort of like a standardized way of deployment of um, the software components. The thing is that Kubernetes was more of an application-oriented thing, and it was more of a stateless type of deployment that it used to handle. But with the coming of um, the stateful sets, as well as uh, persistent volumes, stateful types of deployments are also become a reality, right? And that is probably where the data world is heading. So this is sort of like a shameless plug, but as DataStax, our company is heading in that sort of orientation. So we're trying to provide something like a hybrid database as a service. As a service, probably you would understand it's basically that it's a sort of a cloud type of thing where you would just push a button and then you would have your database, right? Of course, in the cloud world, basically you would have your cloud vendor managing the database for you, or we would be managing the database for you, and you would have it as a service. But if you have something like an on-premise deployment, you would also want a similar kind of methodology that you could provide to the users of the data platform as a service, right? So the Kubernetes type of things would come into picture in that sense. The way to access the database, if you're doing RDBMS, usually you would interact with SQL, but nowadays, like front-end engineers would more opt into like JSON or GraphQL or REST API. So the way that we would be providing is providing an interface so that it would cater to those kind of users as well. And of course, because it's based on Cassandra, it could run in any cloud, it could run on premise, and you could span all those environments as well. Okay, well, that was sort of the things that as a company we are providing, but the base is Apache Cassandra, and as I said, in this future slide, I would think that other databases would be heading into this direction as well. There are a few databases already providing something similar, but on-premise and cloud, providing cloud native kind of experience is where I would say the databases are heading. Okay, so I see there's one question. So in my view, which type of industry workloads, conventional RDBMS will always be the better choice? Okay. Yeah, so I would say reporting types of workloads are more an RDBMS type of thing. If you have multiple tables and you want to do multiple joins and produce a report on that, probably RDBMS or SQL is a good way to do that. And yeah, I would say that would be one thing. Another might be that you would have, well, if the amount of data is not that much, the RDBMS will be able to cope with it. If it's like a few gigabytes, under a terabyte, or maybe it's a couple terabytes, then I think the RDBMS would be okay. But if you're going to handle like multiple 100 terabytes or petabytes of data, then probably RDBMS will not be the choice. Okay. Okay. So that's about it from me.
Well, thanks, Yoshi. Almost on the dots, right? So we got only a few more minutes to go. I see that there's another question on the QA panel. Is that right? Oh no, it's just say thank you. Yeah.
You're welcome.
Okay. Anyway, thanks for the interesting sharing, Yoshi. Right, and I'm pretty sure our attendees today has learned quite a fair bit. Right. I'm not sure why your video is not showing, but that's all right. You sounded great, and the slides look good. Yeah. So with that, I would like to thank everyone for joining us here today, paying attention. Hopefully, we will be able to bring you even more exciting and interesting trends and technologies based on open source in the near future. In the meanwhile, you have a good evening ahead, and I'll catch you guys again. All right. Thank you, everyone.
Thank you very much.